Hello everyone. So now I'm going to talk about section 2.5, continuity. Um, so before come to this section, we have a question that when is limit of fx when x go to a will be equal to the value of fx at x equal to a, which is f of a over here. See that? Um, In other words, when is it okay to just substitute in the value of x equal to a to get the limit, right? So you in the previous section, let's go down, go up a little bit. Let's see. There is some problem that have um, let me see, not this one. I'm gonna say where that's mm, uh not this one. Also not this one. I need to have an example for you guys. Uh, Here we go. This one. So you can see that for example in um, x equal to a, right? I'm sorry, in x equal to 2, what happened with the f of x? You see that if if x equal to 2, then f of x equal to 3, right? But the limit of fx is different. Of limit of x in here is does not exist, right? Because why? Because from the left hand side, the limits go to this point, which is equal to 3, and from the right hand side is go to this point or this hole, we the value is going to be equal to 1. So they are different, and the limits is not exist, they don't exist. In another case, for example, as this case, right? Um, Even though we have f of x, limit of f of x gonna be equal to 4 when x equal to 4, right? But the f of 4 is do not exist because there's a hole here, right? So it is sometimes it could happen like that. It's kind of like you um, you cannot have like f of a always have to be equal to limit of fx when x go to a. So let me go back with 2.5 again. Okay, so now um, now we're gonna try to figure out when it happened, right? When fx equal to when limit of x when x equal to a equal to f of a. Okay, um, and the definition with informal definition of continuity. Okay, um, let f of x be a function and a be a number in domain of f. We say f is continuous at a if the graph of f has no holes, so it's no holes, no jumps, or vertical asymptotes at x equal to a. Okay, good. And b, if f is not continuous at a when we say it is discontinuous at a. Right? Okay, so let's take a look at um, some picture over here. Okay, so the problem A with the graph of a fraction uh, and here, you see that there is a hole, right? So the graph is a line, but there's a hole, and x equal to 2, right? So you can see with this rational function, and x equal to 2, let's make the bottom is 0 and make the f of x undefined. So that's the reason why in here there's a hole on the line as x equal to 2. So I'm gonna say discontinue. Discontinue us. Okay, for this graph at x equal to 2, right? Maybe I'm gonna move down a little bit so later on at x equal to 2. Okay. Okay. All right. Now, what about the second one? I have f of x. This is a piecewise function. Why it's called piecewise function? Because you have two pieces, right? One pieces is depend on 1 over x squared with requirement is x not equal to 0. And the second one is just equal to 1 when x equals to 0. Okay, so you you can see that is go to the positive infinity when x uh, goes approach to 0. See that? Well, that's that is for the using the part A over here from their definition. You see that we should not have the vertical asymptote at x equal to 0, right? But this one have the asymptote. Right? So then we also want to say discontinuous. Oops. Discontinuous. At x equal to 0, right? So let's move to the next one. Let me split it. For this one, again, this one, even though you have, so this one is, there's small hole here, but at that point, x equal to 2, value of y gonna be equal to 1, right? So for this case, we call like a removable. So let's say remove able let me removable. For this graph, it have removable, or you can continue to say that there's a hole also. So then you can just say, oh, there is discontinuous and what? And x equal to 2, right? Okay. Now let's move to the last graph. So you see that this graph have like a a slider, right? Sorry, a ladder. It's just like step and step and step and step. So like you jumping from this one to this one to this one. So it keep going like that, and it's not continue, right? Continue like you go smoothly, and there's nothing when you go on a street. It just the street should be flat or smoothly, or I mean doesn't have any hole, doesn't have any broken line, something like that. So that could call it continuous continuous for this guy, but this one is not, and it's called like a jump function, right? A jump function. Then you're gonna say discontinue continue. This is this con oh my goodness. Discontinuous. This one have like so many discontinuous point, such as like at 0, at 1, at 2, at 3, something like that. So it's discontinuous there. So and I just gonna say this one discontinuous. All right, so let's move to the formal definition. A function f is continued at a number a if the following three police hold. Okay, so what is the first one? Uh, f of a is defined and a is in the domain of f. Okay, limit fx is the axis when x go to a. So you need to firstly you need to have fa is defined. Secondly, you need to have limit of fx when x go to a is axis, and then lastly you need to have two of these limits of fx when x approach to a will be equal to f of a. So if you satisfy three of these requirement, then you can say limit of fx when x go to a is equal to fa, and it is the fx continuous at continuous at a at x to a. So is continuous at x equal to a. Okay. Okay. So continuity. Can you draw the graph without lifting the pen? And then the function is continuous. Okay, yeah. That is it. Okay, when you want to draw a graph, yeah, that's continuous. You're just gonna draw without lifting the pen, and it should be continuous. All right. So let's take a look at example number 16, where its following graph is done is discontinuous, and why? Okay, so if you draw this graph, right, you go like this, and you say, oh, I'm gonna leave my pen, right? And then move to the next one because there's a hole here. Okay, and then keep going. So that means what? So that means what? This one at this point, there is a discontinuous, or there's a hole there, right? And we say like the graph is discontinuous at this point, which is at x equal to 1, right? X equal to 1. So what else? I keep going. Okay, I keep drawing, and then oops, my ink is run out. I don't know. Okay, so I keep going. Going down. And I say, oh, then I don't want to draw down more, right? I just gonna jumping up here, right? And I keep going. But that means what? That means it's discontinuous at this point, right? Jumping, right? So at 3. So then you you have like the graph discontinuous at x equal to 3. Okay, so now keep going and keep going, and I see, oh, there's a hole here, and I got just flip my pen and put a dot here, which mean it is removable, right? Or a hole here also movable, and we also call this at this point it have discontinuous, right? So and then it's keep going. So conclusion, we have we're gonna say we have 3 point that's discontinuity, right? First one at x equal to 1, right? F of x sorry, f of 1 is undefined or not defined. So because of the hole, right? At x equal to 3, the limits of fx do not exist. When x goes to 3, do not exist, right? Because the left-hand side and the right-hand side, they are not equal each other, right? And because of jumping, so the left-hand side limit not equal to the right-hand side limit. This in order to explain why is this continuous, you need to use the formal definition to explain it over here, right? You cannot just say, oh, because jumping something like that. I mean, for explain formally, you should do like this, but and then at x equal to 5, you're gonna say limits of f of x when x go to 5 that not equal to the f of 5. Because why? You can see the left hand side and the right hand side limits will be at this value. I'm not sure what is that gonna be, but I think but I'm pretty sure it's different with the f of 5 because the f of 5 will depend on this removable point, so they are different, right? You can see the value of y is different. Okay, so so that is, they are the 3 points. discontinuity. Okay, so let's move to example number 17. Functions weak continuous for all real number. Okay, so the first one is linear function, right? For the linear function, is it like Lx equal to m of x plus b is just keep going down, up, or something like that. It's just always smoothly. There's nothing. There's no hole. There's no jumping. There's no removable number, something like that. Then it should be continuous. Also, polynomial function. You can see like something like parabola, something like that. It should always smoothly going up, going down with the shape curve, something like that. And there's no hole of that. No no discontinuities. Also, exponential function is also always continuous, right? And some trig function we call like sinusoidal. I don't know how to pronounce that, but anyway, trig function such as y equal to sine x or y equal to cosine x, it's also going to be continuous, right? And even the let me see, tangent of x. I don't want to. I don't. No, I don't take that in here, but yeah. For the size to be also sine cosine should be also continuous. And now let's move to the discontinuous function. Firstly, is usually you're gonna think about is rational function. And in rational function, usually the one um, that make so I say rational function. Rational function usually at the point that make the bottom equal to 0, right? For example, here, right? I have x equal to 2, and that make the bottom equal to 0. So then that should be undefined, and at that point it's going to make the graph make the graph um, discontinuous, right? Also, for another function you can consider is piecewise function. Piecewise. Okay, piecewise function could also make discontinuous functions, because sometimes it's make like a jumping function, something like that. Um, so yeah, so for example over here you can see that the left hand side limit to the of x when x go to 0 is not equal to the right hand side limit of x when x goes to 0. So that's make the f of limit of f of x when x goes to 0 is does not exist. Okay, so it's also going to be not continuous. Okay, so I say for the first function over here, there is a vertical, vertical, vertical asymptotes. F x equals 2, right? Okay, and vertical asymptote that make the function never cross the over, right? Function will never function never cross over vertical asymptote. So this is vertical asymptote. Okay. And for this one is jumping function, jumps function. So I'm going to say jump and this continuous. Really, s x equals 0. Okay. Okay, so let's move up. All right. Okay, so we have theorem number 2. If f and g are continuous at A and c is constant, then the following function are also continuous at A. Okay, so first one, you have addition or subtraction of two this function, so fx plus or minus g of x. Okay, or you can like reverse it like g of x and then plus or minus fx, same. And number 2, you can multiply a constant number with the function fx or g of x. It's going to be also a new function continuous at A. Number 3, the multiplication of between fx and g of x will also is a function, continuous function, or like a function continuous at A. Okay. Number 4, fx over g of x will be also continuous at A when g of A is not equal to 0. Okay. So it could be discontinuous when g of x equals 0. So in this case, the given was g of A not equal to 0. So there's maybe a point that make bottom equal to 0, and at that point that's will make the function uh, discontinuous. Okay, so composition function f of g x. Okay, so remember this one. I know that some of you still confused. What is that? But I just want to remind you that it actually mean the function of f when input is g of x. Remember that. So yeah. So that's also going to be a continuous function. Okay. Now, for the proof, you're going to follow from the Leibniz law, and yeah, and you can easily prove for those functions. And most functions are continuous at every number in their domains. Okay, so number 3. The following types of function are continuous at every number in their domain. So firstly, function with a polynomial. So what is the example of a polynomial? Let's say 2x squared plus 2x minus 2. I like number 2 because my name is 2. So this is also like a quadratic form, right? But yeah, it's also called a polynomials. So domain here is what? All real number. So all real number. Okay. Or from negativity to positivity. So either way you can write, right? What else? Rational function. Okay. So rational function could be also for example, like 2x plus 1 gonna be over x squared minus 2. So but I want to have a domain with denominator norm in here is not equal to 0. So let me what x squared. Let me change this number 2 become 4. So I can have for you easier. Minus 4 equal not equal 0. We give me x not equal to positive or negative 2. So you can use square root both side or factor it out to get the positive and minus negative 2. Okay, so that is for the domain. Okay, so what else? Root function. Okay, square root of say x, and what is the domain? Domain in here is I need to have uh, the radicand is uh, is always greater than 0. So maybe I'm gonna note like this. Inside of the radical here, which is the radicand, right? And I need the radicand have to be greater than or equal to 0, right? The box here could be many things. It's not only x. It could be like x squares, something. Yeah. So because this is only x, so actually in this case x has to be greater than or equal to 0 for the domain of this case. Okay. So I just want to make sure if in another case, then you should know that the radicand is a all box inside radical has to be greater than or equal to 0. Now let's check. You let me try like sine 2x, right? Remember that's for trigonometric is gonna be all real number, right? All real number. So positive if you need to negative if you need to positive negative. What else? Inverse trigonometry. So let's say cosine inverse of I don't know, maybe x plus 1. Okay, for the inverse of this case, if you take a look at the decimals, you can see that it switches from negative infinity, negative 1 to positive 1, right? The value of x should be from negative 1 to positive 1. Remember that the inverse of the trig in here is actually like the value of the cosine or the value of the sine. And remember that since it's the value of cosine or sine, it should always just come from negative 1 to 1. That's all. Okay, so what else? Exponential. Okay, so exponential, I have let's say e to power 2x. Then I have exponential could be like always all real number. So negative infinity to positive infinity. Always. Okay. And lastly, logarithmic gonna be log 3x log of a box over here. With this argument, is a box, is always greater than 0. That is a requirement in here. So actually, I need 3 of x greater than 0. We're gonna give you x greater than 0 for later on, right? Okay. So now, main application, we can compute many new limits just by substitutions. Okay. Remember that. A ball over here. Where that's a ball in the first page. We did have a question that when can I just when is the limits of x when x goes to a can just be substitute a into the fx. Then that means that when I see the f of x is continuous, f x go to a, then I can just substitute into it and get the limits. Okay, so in this problem, example number 19, limit of x go to of x multiplied by square root 29 minus x squared. And I have x go to 5. Okay, so firstly, I know that this x is a polynomial, right? Polynomial. And for this part, it is a radical function, or root function. Let me say root function. With domain is what? You need to have like 29 minus x squared greater than or equal to 0. If you try to solve for it, it's going to be a little bit long, but think about if you plug x equal to 5 into this, right? Plug x equal to 5. We have 29 minus 5 squared, and then that equal to 29 minus 25, which is equal to 4, and that is greater than 0. That is good for the domain. So x equal to 5 is in domain, right? In the domain. So since x is in the domain, x equal to 5 is in the domain, then I just direct substitute, right? So I have limits of x multiplied by square root of 29 minus x squared, x equal to 5, equal to 5. Now all the x change to be 5, right? Square root of 29 minus 5, everything squared. And now you're going to have 5 times square root of 4, which equal to 5 times 2, and it equal to 10. That should be the answer. Okay. Similarly, in example 20 here, I saw that limit of ln 1 plus x. So if you substitute 2 into it, I have say limit of I'm sure I'm gonna check inside first. If I have ln of 1 plus 2, what happened? That's gonna be ln 3, right? ln 3, right? And that is in domain, right? So you can just make it equal to ln3, because remember that's for the log function. You have to just make sure it will not, I mean, it always has to be greater than 0. That's all. But in here, 3 is x equal to 3 is greater than 0 is in the domain, right? So now let me move to B. Okay. So in B, if I have like, if I substitute x into here, right? I have ln of 1 minus 1, that equal to ln of 0. But x equals 0, that's not in the domain, right? I need x is greater than 0. So can you direct substitute? So for this case, you can have limits of ln when x plus 1 plus x, when x go to -1, will be negative infinity, which also called undefined. Okay. You can also check it if you want on the Desmos about this function. Let me try to show you. Okay, so Desmos. So y equal to ln 1 plus x. So you can see that when x try to go to the -1, what happened? So here, let me use annotate. Here is a -1, right? So -1 is have like a vertical vertical asymptote, and the graph just go along with the line x equals to -1, right? So that is my this graph is undefined, and it's keep going down, so that we call what's it called, net infinity. Okay, the limits do not exist. So let's move to the next page. All right, so I'm gonna let you guys to try to do the exercise 11 and 12, and if you and we will work on that, and 13 also. We will also work on that in the class. Okay. So Okay, so now we're gonna talk about intermediate value theorem. Okay, we also have um, initial as IVT. And suppose f is continuous a on the interval a to b. So let's see the graph over here. Here's a, here is b, right? And you see the graph is in the blue line, right? Um, you see that it's continuous on A to B, right? It's just no hole, nothing's jumping from A to B. You don't see that. What else? Let n be any number between A and B. Okay, so they choose here at the value of n for the y value, right? Um, where f of a not equal to f of b. Okay, so f of a was here and f of b was in here, right? Then there exists a number c in the interval from a to b such that f of c equal to n. Okay, so there is exists a c, right? That in the uh, uh, open interval from A to B, that's f of c will be n, right? F of c will be equal to n. Okay. In this graph, let me see. So what is this theorem IVT saying? That a continuous function take on every intermediate value between the values of fa and fb. Okay. So in this graph, do you see a and b on the x-axis? So over here, right? A and b, and fa and fb on the y-axis. A and fb on the y-axis. So here, what IVT is saying, for all value of c between a and b, c is in here, all the value between a and b, right? There is a point on graph that give a y value between fa and fb is labeled n in this graph. See that? So okay, so here is example 21. We try to prove that there is a root, right, of f of x equal to 4x cubed minus 6x squared plus 3x minus 2. We in between 1 and 2. So actually we will use the intermediate value theorem, and it's actually from intermediate value theorem, it will locate for me or estimate for me where the rules of the function should be, right? So that is excellent use for the IVT. Okay, so question, what does it mean to have a root of a function? The root function is mean that to find some value of x, such as f(x) equals 0, right? That's like that's a solution when of the function when f(x) equals 0. And then the important point is our function continuous, right? And then yes, because see, it is polynomial, right? See that it is polynomial, so then it is continuous. And now we can use IVT because before using IVT, you have to make sure f is continuous on A to B. If you see a rational function, it could be discontinuous, but you have checked if the question for the locate the root from A to B. You can check if from A to B there is no discontinuous point. Then you can still apply IVT. Okay, so let's because it say like between is A is B, right? Between A and B. So we're gonna let's try f of A first, right? This is f of A, and then f of B also, right? In here, f of A, which is f1, gonna be, you're gonna substitute it into the function, right? Which is 4 times 1 cubed minus 6 times 1 square plus 3 times 1 minus 2. And use the calculator, you actually finally gonna guess -1 or negative number. Okay, when you have a negative number for the first one, now you go to the second one when b equal to 2, right? Then f2 gonna be equal to 4 times 2 cubed minus 6 times 2 plus 3 times 2 minus 2. And use calculator, you're gonna get a 12, and that's greater than 0. And seeing, if you notice that you have taken two x values, which is a equal to 1 and b equal to 2, and found that you have f of a will be equal to -1 and f of b equal to 12. That mean x, there is a value of x in between 1 to or I'm gonna say there is a value of c in between A and B. That makes f that make f of x or f of c going to be in between -1 and 12. So the IVT said that I can pick any value of x in between 1 and 2, and we guarantee that I can find a value of function in between f1 equal to -1 and f2 equal to 12. So so you can pretty sure that you can pick our function value to be 0, right? Because why? Because it was come from a negative number to a positive number. So it have to go through 0 later on, right? Like, let me draw the graph here. You can see, right? Any graph that like have, like for example, you have A here was -1, something like that, -1, right? And and you have B was somewhere over here, and that is 12, right? It means what? It means that the graph has to go through a value that make Lx equals 0 before go to 12, right? So 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 that's the reason why IVT help you to locate there is a root that that's certified for the function. Okay. Okay, so let's move to the last page. Over here, exercise to try 15. Okay, actually, I'm gonna solve this problem for you, and then you're gonna try number 16. Okay. So we use the intermediate value theorem to show that there is a root of the given equation x4 minus x minus 7 equal to 0. So first thing, are you sure this one is continuous? Right? You need to make sure this is continuous on the interval from 1 to 2. Yes, it's continuous because it's polynomial, right? Polynomial. Polynomial. So continuous. And what else? Now find a root of f of x. In this exercise, I'm guiding you through the step. Okay. So seeing is continuous, then I can apply IVT. So IVT. Okay. Now find f of 1. Why I choose f1? Because here look at the interval. I have a is 1 and b equal to 2, right? See that? So I need to find f of a first, which is f of 1. Okay, so I need to substitute a equal to 1. Substitute 1 into the function. So 1, 4. 1 to the power 4 minus 1 minus 7. And what is that equal to? 1 minus 1 is 0, so it's 197. So this is less than 0. Okay. What else? For 2. Okay, so 2 to the power 4 minus 2 minus 7. What is it gonna be? So 16 minus 2 minus 7 gonna be 7. It is greater than 0. So anytime you see like f of a and f of b, they are like different with the sign, right? One of them is negative and one of them is positive. Then you know that there is exists a root in between the interval from a to b, right? So, yeah. So then f1 in here was -7, f2 in here going to be 7, and then in order to complete, you're going to say there must be a value of c in the interval from 1 to 2 that gives you f of c equals 0, and that there's a root, and you're done. Okay, so I would like to let you to do exercise number 16, and we're gonna talk on it in class later. Okay, see you in class.